This is the final day of this week, the final session, and we are very glad to have Emmanuel as presenter of how could we use new innovative tools for our daily work. Emmanuel has a lot of experience in data analysis, etc., 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 etc. And Emmanuel, could you please briefly introduce yourself and show the vast experience that you have in crazy fields?
Yes, so good afternoon, thank you very much for coming. I'm very afraid, but I managed. So I'm Emmanuel. I have a background in particle physics. I did a PhD and research in artificial intelligence. Then I worked in various places, notably in a shipping company, doing artificial intelligence optimizations of things. And then Florentin found me and brought me around. So, don't know if you have any questions. So, I'm going to present something about aerospatial images and how we can process them, what we're supposed to do them. I was a bit unsure of what exactly it was we wanted to focus on, so I did a bit of everything. Don't hesitate to ask if you have any questions. As my previous colleagues said, there are no silly questions, there are only questions with easy answers. And if you have those questions, probably someone else in the audience also has them, so you're doing everybody a favor by asking. So don't hesitate to interrupt and ask if you have any question. And we can also discuss further after the presentation. I apologize in advance if somebody is actually more experienced in one of those topics than I am. Please bear with me. And I'm going to start. So we're going to talk about where the images can come from, what type of images we can gather using various sensors. Then I'm going to quickly explain how computers represent images, what it is to them, and then explain how we can then use those representations to extract meaning, and eventually try to see what the future can hold for us, where we could go, and possibly start some blue sky thinking and discussing ideas. So, does anybody play video games?
Especially this one.
Aha!
The new one is out now.
Of course we play. Okay, so you can see Space Race Project, which launches a small satellite into orbit, reveals the geography of any unexplored corner of the world, and marks the first step towards the science victory. So when you launch a satellite, you can see everything, you can see all the world, you can see how things are. I wish that was true, but it's simply not the case. It's more complicated than that. So, what a satellite is. Typically, okay, first there are lots of satellites. The first satellite was Sputnik 1, it's a bit larger, something like that. We now have satellites like the International Space Station. You can live inside it, so it's much, much bigger. So it goes without saying that satellites with such vastly different characteristics have also very different capabilities. So I want to attract attention to one specific example, which is in the Copernicus galaxy. So a galaxy is a team of satellites working together to achieve, to realize one specific mission. So the Copernicus galaxy is in low Earth orbit. So what you have to understand, it's a basic fun physics fact, satellites work like a slingshot. You basically run in a cycle around the Earth, and the acceleration you get from going in cycle pulls you away from the Earth and counterbalances the attraction of the Earth. And so, the closer to the Earth you are orbiting, the quicker you have to do it. There is one specific place where the speed of rotation of the satellite matches the speed of rotation of the Earth, which is called geosynchronized orbit. If you go lower than that, you go quicker than the Earth. And this is the case for these satellites. So they are actually moving with respect to the surface of the Earth quite quickly. And those satellites, the Earth observation satellites, typically are in the Earth rotates like that. The satellites are going to rotate like this, so they can map the entire Earth. There are several satellites doing the same thing at the same time, so you have more passages of satellites during the day. And the same spot on the Earth is observed several times a day, because the satellite is going to go directly above it and then slightly on the right, but you can see it on the photograph and so on. So you can actually have several views of the same place during one day. So one example of a mission like that is the satellite Sentinel-2 of Copernicus, but you also have a number of commercial applications. So companies that launch satellites are very willing to sell you the images for a price. Now, we also have airplanes. So typically those are small general aviation craft that are fitted with sensors, so for instance a camera, and they can also map territory and take photographs with it. You also have drones. So this is one example. Just like satellites, you have drones of all sorts of sizes. So you have the small toy drone that basically fits in your hand, and the larger drones are big, like airliners, like 737 or something like that. Those are the long endurance military surveillance aircraft, which can very much be used for mapping territory as well. But typically you would be using something of that sort, so either a quad or 6 copters or something like that, or vertical landing fixed wing aircraft. Same thing, those are cheaper than aircraft, than actual planes, manned planes, and they typically have a lower altitude. But in general, there are ways of combining all those platforms. So you have various sorts of satellites, and you can have high-altitude drones, you can have balloons. So all sorts of ways of mapping, surveilling the Earth at any time. Now, we have those platforms to carry the sensors, but what sort of sensors are we talking about? So, one interesting one is the radar. So radar means radio detection and ranging. So the idea is that you send, everybody already knows that, but I'm just repeating for the sake of completeness. So you send a radio signal in the air. If it meets something, it's going to rebound. You're going to get the echo, and from that echo, you can say there's something there. It's in this direction, and from the time that it took for the rebound to go and come back, I can tell the distance. It's very important. It's very important to filter the signal. The radars in the 1950s, for instance, had a button marked pigeon, because that was the button to remove the pigeons from the screen. Actually, you can really detect very small objects and also, non-metallic objects, just birds. When you think of a stealth aircraft, the stealth aircraft actually is visible on the radar. The trick is that to see that aircraft on the radar, you have to remove all the filtering and you're going to see all the pigeons, and the stealth aircraft is lost in a sea of pigeons, so you don't know where it is, which one it is. But we use radar to detect clouds. That's for meteorology. So it's very important to have algorithms to tell what it is that the radar is seeing. And it's not obvious in films. You know, it's very easy. You can see beep, beep, beep like that, and you have one point, and you say, here it is. In reality, it's more complicated. So it's in the Earth observation radars are in the K band. So it's about 1 centimeter. So I'm telling that not because I have gone mad, but because it gives us an idea of the resolution that you can have. A sensor typically has a minimum resolution approximately the same as the wavelength that it's using. So you can have about 1 centimeter, you could theoretically have about 1 centimeter resolution. So it's a very fine resolution as far as Earth observation goes. In practice, it's going to be lower than that, but still, it's very usable. One big advantage of radar is that it works at night, and it even works through clouds. So you can see your territory any weather. Another advantage is that since you are lighting your objective from above, and you are the light comes from you. It's a radio light, but that's basically you sending the signal. You have no shadows.
Excuse me, you said we could ask questions.
Yes.
About the band.
Yes.
Could you once again? What is the centimeter? What does it show?
Yes. Sorry.
How much off it is? Or what?
No, it's the size of the size of the object that you can see. So, for instance, if I was using a radar, that object would simply not be. It would be transparent to the radar because it's too small. But you could be seen because you are larger than 1 centimeter.
Oh.
The radio waves are electromagnetic waves, just like visible light, just on a different scale.
So this is not wavelength.
Yes, that's it. Yes, that's what it is.
Wavelength.
Yes, that's what it is. The wavelength conditions the resolution that you can have.
Okay.
You can never, using a 1 centimeter radar, you can never see a 1 millimeter object. Now, if we use LiDAR, we are doing the same thing, but with visible light. So visible light is much smaller. It's in the nanometer range. This is interesting because you can have 3D models of what you are seeing, and you can even map trees using this technology. So you can see through the tree canopy, but you can also see the shape of the tree. It's very impressive to see. This works at night because you are sending the light, but it would not go through clouds, so you need clear sky. There again, you have no shadows because you are sending the light itself. Now, you could simply take a photograph. So in this case, you would be using the same visible wavelengths, so in hundreds of nanometer scale. So you have the resolution that you are accustomed to as a human being. That's the reality of the health of trees. You can actually make 3D models by taking photographs from various angles of the same object, and then interpreting a cloud points to build a 3D model. That's what's called photogrammetry. It's quite fun to try. You can try it at home. It's quite fun. Or even with a smartphone now. For this, you need a clear sky. So we obviously not go through clouds. You see the clouds. And the image features shadows. So if you are not sending the image, you are not sending the light. It's the light of the sun that is reflected from the object, you see. So that means the hour of the day is going to change the color of the light and is going to put shadows on your object. So if you see the same object at different times, you will need to adapt the images to remove the shadows, to adjust the colors for the computer to be able to compare images. Questions?
So basically, these are photos.
Yeah, absolutely. These are literary photos.
And the ones before were wavelengths, radio or light.
Yes. So basically, you have two things. You can either illuminate an object using a thin beam of electromagnetic waves, and that you can do either in radar, so in radio, that's radar, or with a laser, which then is a LiDAR. And then you can also simply capture the light that is reflected from the object, the light coming originally from the sun.
So radar and LiDAR are in black and white?
Yes, exactly, because you are sending an image and just getting an echo. So you can do that in different wavelengths, but you're getting a black and white image.
You're getting back a strength of signal.
Yeah, so it's not a black and white, and just its shape of the things, yeah?
Maybe. You can imagine that, for example, like a sound, that the strength of a sound when it's coming back, like radar, and then it's the matter of processing to understand, make use of what the signal that you get back. LiDAR puts in all the a point. It creates a point cloud and puts it in 3D sort of axis.
Yeah, it's basically what a bat or a submarine do with sound using sonar, that it does with electromagnetic waves.
Same with whales and so on.
Exactly. Okay, so just a word about the pricing. So I've just checked. I didn't want to mention any particular commercial operator, but typically you can get new images for 20 euros per square kilometer. Lithuania is 65,000 square kilometers, as you all know. And so that's actually going to be one shot that is fairly expensive. You can also have yearly subscriptions. Typically, they will bundle open source data, such as Copernicus, with certain commercial information. And this way you can have a very strong coverage of any place you want.
Which is the most expensive service?
Sorry, the
yearly subscription.
Yes.
Which is the price can fluctuate from to 15,000 per year.
This is for photogrammetry. It's just depending on the resolution.
That would be for photography. So yes, it depends on the bandwidth you're going to use, and also some of the services will include processing of the image. So depending on how often and how large the sample you want to study is, you're going to need something more or less robust, industrial, I would say.
Yes, sorry.
Yeah. No, good question. Okay. So those are actual prices from one of the areas. Sorry.
Does it cover the historical data?
Yes. Yes, it does.
So it means that we can have data from, for example, 2011, 12, and so on.
That's a very reasonable date. I can't guarantee that it's the case, but yes, I'm pretty sure you can. So you can do time series. Okay, so I want to show you briefly, it's very simple, how computers see images. So basically, you have a table with numbers. So you get one number, another number, another number, and that makes a row. And then in the memory of the computer, it's going to just go like that, but you can imagine in your head that it's actually going like this, so you're going to have rows and columns. And it would create a table matrix of numbers. If you have just zeros or ones, you can encode an image of this one. Now, if you have more values, so either you, in the computer typically is going to be 0 to 255, but you could also represent that as, rescale that, so you could have 0 to 1 with smaller intervals. You can get grayscale. And now, if instead of just one table, but three, one for each fundamental color in the additive color space, so red, blue, and green, you get the same image, but in color. So, very simple. But that entails that images are basically tables of numbers, and that the computer can process with math. So you have tables of numbers, so that's a matrix. That means you can do any operation of linear algebra, which is your favorite subject, of course. So you can, of course, compare how similar the matrices are. You can say this is almost the same, just a few points have changed. Or it's the same but skewed a little bit, something like that. You can say, you can also apply artificial intelligence processing. We're going to see that a little bit later to give you an idea of what it looks like. But you can then interpret images saying, okay, this cluster of values here constitutes an image which represents an object that interests me. For instance, a pile of garbage inside in the forest where it shouldn't be. So, we're going to a little bit more detail. So, with radar or LiDAR, so the ones where you illuminate an object and you record time, you can have elevation data that is, well, okay, distance from the ground. You can have that anytime that is also by night. The radar will work even if the weather is poor. It will not have shadows, which makes for an easier processing. You can skip the step where you remove the shadows, which is a bit tedious. And it can be very precise to the point that you can actually reconstruct a tree into a 3D model by typically LiDAR cloud point. The optical photography is reflection in the visual spectrum, so it needs clear weather. It needs to be in daylight. You will have shadows. You will have a good precision to the point that you can actually also recreate 3D models if you like. It's usually cheap. And since it is or can be in color, you can get more context. So you get the time of the day from the shadows, the colors can give you clues as to the weather, as to the time of the day, as to things like is something burning, is something healthy, and so on.
So,
Yes.
we usually have a problem with quarries, the legal pits and so on, and not what's called quarries probably. So, and we have problem with calculating the, for example, sand which was taken from the quarry.
Mm-hmm.
So, in this case, the best way to calculate it is to know the data, how that place will look like before.
Yes.
Because probably LIDAR is that thing which can show us the elevation.
Yes.
So in this case, the best way is to use LIDAR.
It could be a way, but you could. So I mean, LIDAR would be absolutely perfect for that. You could also do that optically, for instance, by analyzing shadows. For instance, you have a quarry. I go with my little spoon and I take some of the sand.
Yeah.
So I'm going to leave a hole.
Yeah.
You might not see it clearly from above just by seeing the light, but if there is a shadow, the hole is going to be shallow. And you can get you can detect the hole, you can say exactly where it is, you can say exactly how deep it is, but it's very powerful. But then again, that's...
Because in our case, we really need to have cubic meters.
Yes.
So it's possible.
Mm. Yes, so, but LiDAR would be ideal for that. Absolutely. Mm. So, you have your image. Now, as I said, the satellite does this thing. So, you can't control the satellite. Once it's in orbit, it doesn't move. It can move a little bit, but for very specialized, they're not going to move the satellite for you. That's not the thing. So you're going to have to make do with the satellite passing above your target in slightly different angles. So you will have to align your images. So in this case, you could see an image of an uneven ground that needs to be projected into a flat surface for interpretation. So it's very. It's just to give you an idea of the sort of pre-processing that is needed for the images to make sense. Then you can, having your images and having aligned your images, you can have several passes at different times, and you can follow the evolution of what the site looks like. So it's fairly obvious. I'm going to give you an example here. Yearly views of a section of the Amazon. So you could detect the removal of the trees and the construction of fields, I suppose, from this series of images. And it's very clear that the dark green parts are getting smaller and smaller. So this requires very little sophistication. You can simply count the pixels and say, okay, something's going on here. Then again, you could decide to go further and deploy artificial intelligence tools. So, for that, you would need to learn features in the images. So I'm going to give you two examples of artificial intelligence tasks. One is unsupervised learning. In unsupervised learning, you give a number of samples to the computer, and you ask the computer to find commonalities in the samples, to basically describe the data and say, okay, I see that many of the objects, points, phenomena, I see, some behave like that, and some behave like that. You have a bit like this, but those two are clusters that look alike. It doesn't tell you what it is, but it's just going to say there are significant populations having the same characteristics. Supervised learning is when you know what those clusters are like. I mean, you know what they mean. and you say, this is an example of what I'm seeking. And then the computer is going to say, okay, I find other patterns that look like this in my new sample. So that's a good way of classifying this under predetermined labels. It can also be used to learn features from the labels. That is, you could have. I'm trying to find it. Okay, I'm going to give an example from my life. At some point, I was working at the shipping company, and we had containers. Some of the containers would go on the ship, arrive in a port, and nobody would claim them. They would just sit there and never go through customs. And usually that was not a good thing because it's quite expensive to park a container. And when you have things like potatoes or perishable goods inside the container, you can imagine that several things happen. In the end, somebody has to clean them. So we don't want that to happen. So the question was, we have this list of containers, and we also know who ordered the container, on what date, what they say is inside, where the container is, and where it's supposed to go. Can we, from that, tell which containers are likely to be abandoned? So we got data about the containers. We got labels saying this container was okay, this one was abandoned, this one is okay, this one is okay, this one is abandoned, and so on. We run through, we run this through the computer, and the computer says, okay, when there is a combination of ports and content and so on, that is indicative of a container that could be abandoned. And then when you give just the parameters of the container, it flags you the most suspicious containers. In reality, it didn't work because we didn't have the information that actually was actually determining that the computer would be abandoned. The information was not in the data. That's the difference between information and data. But in principle, the system could work. If you get the good data, if the information is in the data, the system is going to make predictions from the experience it has in the training test. So that's what supervised learning can be used for. To give you, sorry,
about the supervised learning. So just imagine we have 1,000 calls to our hotline per year, and we carry out some kind of investigation for these 1,000 calls, and they are of similar nature.
Yeah.
And then we have results of what has happened, whether violation was found, not found, etc., etc. And we have all the phone calls that were recorded. So, in my imagination, I think that we could have an AI tool that analyzes all the phone calls, the interaction between our person and the caller, different information provided, and match it with our results, and then say after we have finished the call, it is 92% likelihood that with this information that the caller provided, we are going to end up in that situation, whether it was successful or not.
Yeah, exactly. Yeah. That's very much it. The computer is going to be trained on what you have recorded and on the assessment that you have. And then when you give a new phone call, the computer could, in theory, say, oh, this is going to be a good one. Or say, no, okay, that's all right.
And how far are we from this tool practically?
In the sense of
In the sense of
being able to build it.
It
depends. Sorry, it depends on whether you have the data on the. If you have the past data where we can run through what Emmanuel described to see fruitful, not fruitful, and whether these characteristics which are found to determine to be good predictors of fruitful, not fruitful, can be identified through the information given by the caller.
I think yes. I think we have data for 2024.
And it was how many? 20,000?
No. It's 12,000 calls.
Nice.
Yeah, it's a good sample. It depends what you are seeking, and it depends what data you have on the thing. It's typically, it would be difficult, for instance, to process the actual recording, the actual sound. But I suppose that you are taking notes, and some of the notes are in numerical or binary format. So this is easy to process with the computer. And then one thing to be mindful of is how unbalanced your sample is. Because if you have 99% of your calls being actually innocuous and only 1% giving an inquiry or a claim or something, you need to rebalance if you give that to the computer as it is, the computer is just going to say, okay, I see that in most cases there's no problem, so there's never any problem, and I'm right 99% of the time. I'm a genius. So you say, okay, now I really want you to focus a little bit on those 1% because. So you then manipulate your training set to duplicate the 1% entries until they make about 50%. And that enables the computer to train better. But it's really just, it's really technical. Sorry, yes?
And when a computer gives an answer, for example, this caller might be lying or this caller might be true, does it also give reasoning on what kind of arguments?
Yeah, what kind of parameters were there?
Depending on the algorithm you choose, it could be, yes. So one of them I like, that's actually a very brilliant question. The AIs we have that are in fashion at the time now are what we call deep learning AIs. So these are neural networks, so it's one type of algorithm, and deep learning is a way of putting lots of layers of neurons, and it becomes very complicated. It's very powerful, that's why we like it, but then there are so many parameters inside to provide the answer that they become very difficult to express. And in this case, the computer basically tells you something, and you say why, and you say, yeah, okay. I'm doing my best to my best Florentine impression. On the other hand, you have things like random forests. So a random forest is, actually a decision tree, let's say. A decision tree is going to take all of the parameters you have, assign weights to those parameters from the training set, and then it's going to run your specific example through those parameters, combine them, and say, okay, I arrive at this level of, it's going to be a problem by that percentage, and then you can say, why, and it's going to say because there are this parameter and this is, when this is present, it increases the probability by that many percentage, and when this has that value, it correlates in this direction by this strength, and so on. And you can really recreate the decision. That's one of the algorithms that I like, because it's simple, it's quick, and you have this explainability. To say, term. So yes, explainability is very important. It's not only an intellectual tool for geeks, it's really an issue of democracy at the moment. So it's an excellent question, really. Any other excellent question? Okay, so I'm just showing to you what a training set looks like for a simple, typical task in computer vision. It was actually developed from, I think, a postal service. They wanted to be able, they wanted the computer to be able to read handwritten numbers. It's very useful for a post office because you have those zip codes. So this is what the training set looked like. You see the 0 here, for instance, is different from the 0 here and from the 0 here. And it's intuitive for a human. Okay, these are zeros, and but what is this? And for instance, the 4 here is quite different from this one. We know that, but the computer does not. The 7 can even have different conventions. This is a European 7, this is an English 7. This is a badly written 8, this is a badly written 8 in a different badly written way, and so on. So, in this case, we would take a part of the sample, say this part. We would give the answers to the computer, so this wiggly thing is actually a 5, this is a 3, and so on. The computer is going to say, okay, I see that all the 4s have a certain commonality. There is a vertical line and some squiggly thing around it. And when the computer has learned the parameters that are common to all the zeros, all the ones, all the 9s, you give it this part of the table. You're going to say, okay, what is this? It's going to see, it's an 8. No, it's a 2. What is this? It's a 3. Yes, it's a 3. Well done. This, and so on. And how well the computer does on this part of the sample is a way of measuring how well the algorithm is doing. That's typically how computers see the world. But then, you could very well give your computer images of queries, or images of forests healthy, or forests intact, or with illegal logging, or normal fields versus fields where illegal dumping has occurred, and so on. So, for the future, what I could imagine from there, with my uneducated perspective, because I'm not an environmental expert like you are, I think there are 2 dimensions where we could explore. One would be to go for more depth, that is, going into more specialized applications. For instance, we could use in the almost visible spectrum, we could use thermal infrared imagery that would allow us to see fires. It can even be used to see smoldering, so fire that is not already restarted. We could see emissions of particulate matter, so that would be air pollution. That would be indicative of either fire or of some other sort of industrial activity. We can use spectroscopy, that is a technique that analyzes the light to see spectral band that are indicative of certain chemicals. All chemicals have spectral bands, and they block that band from the incident light. So by analyzing the light, you can say, okay, what I'm looking at is made of something. Historically, somebody looked at the sun and said, okay, there are spectral bands that I don't know. So there must be something in the sun that we don't know, and I'm going to call that helium. It's going to be an element associated to the sun. Okay, it turns out that helium is actually quite abundant on Earth, but we had not detected it because it's inert. But by spectrometry, you could see it even a long distance away in the sun. So that could be used for instance, analyzing plumes of smoke. I've put the references of various scientific papers just to prove that I'm not making things up.
And for spectroscopy, what type of, I mean, this is with aerial what is the, okay, we understand the concept how spectroscopy works, but then we need to look from somewhere.
Yeah.
I mean, if we have a smoke here, which is already visible, that's one situation, but what we want kind of automated. So is it with satellite imaging radar? What
that's something you could do with a satellite, yes.
With satellite image?
You could do that with a satellite. You could also do that with a drone or with a plane. It's really, you just need an image sensitive sensor, so basically a camera.
To detect what?
Smoke, fumes from, so in theory, if we have a known sources of pollution which were permitted, and we know exactly where they are located, and we more or less know what are the permitted pollution types, and even the quantities. And if we have this image, the same image from day to day, we can detect if this smoke gets any kind of, different.
Yes, absolutely you can. Yes.
Not too bad.
And the idea with the call center is, I think, really interesting. If you have the data set available and the recording scheme and the thing which the staff is using to record the characteristics, you can send it to Emmanuel and we can have a look personally.
I think that the manual recording scheme is poor.
Okay, so even poor. Let's see. I mean, let's see what's there.
Okay.
And other things would be, of course, to determine, what could be the next manual recording, so that in the future it becomes possible.
But I mean, well, transcription, automated transcription is getting better. A year ago, in Lithuanian, it was, well, a nightmare. Now, it's half bad if you set it up, to transcribe your Teams meeting. So we are slowly getting there, so it might be possible to get those recordings and really set it, well, let an algorithm run through them, transcribe them, and then work with text and the original text of the call. So that way we could get quite interesting results.
Or it can be some kind of keywords.
From the transcription, you could then process the transcription to get numerical indicators about what's been said, and from there you could then.
But it's a lot more steps. It's a bit like we had the discussion this morning at the food agency, food and veterinary, about there are things which are possible, there's technical possibility, and then there's cost. Two different things. So the transcription itself might not be the most difficult, right? But then analyzing the transcripts to find some interesting data, I mean, just can be examined.
But we already have the forms that the call center operators fills out, and hopefully it has the keywords. That might be a starting point.
Absolutely. So that was the notion of getting more specialized applications. The other possibility would be to gather more information. That's what we call data fusion, but it's just a way of saying, I have data, you have data, let's put our data together and make more data. So multispectral data fusion, that's a big word, but essentially it's say, okay, data fusion, and multispectral just means you have LiDAR information in green, I have optical recordings, you have radar, so we have lots of images, we put them together, that's multispectral, several sectors, nothing frightening actually. Centralized processing for information coming from various platforms, various sensors. You could try to get real-time updates, or real-time, you would need to define what you mean by real-time. Is it daily, is it half daily, is it something like that. But you could have regular passes by drones to complement the passes by satellites and so on. You could share information with other agencies, perhaps, maybe the police or maybe the Air Force has something that they can share. Maybe NATO has something, I don't know, the ESA probably has. And you can do all that, but then that creates lots of information, so we also need to be wary of how intrusive we are towards our citizens, because from the sky you can see lots of things, and we don't want to intrude into private lives, and there are regulations for that, so we can implement the regulations to make sure privacy is respected. And that concludes my presentation. If you have questions, I'm delighted, and I hope this triggers discussions and ideas.
Sounds that we will be no longer needed.
Oh, no. Okay, so something I already said this morning. These are tools, and you are humans. That's completely different. These things are at best a monkey on your shoulder. They will help you, but they will not replace you. They will flag things to check. They will tell you the probability of something is increasing or decreasing. That doesn't say what's actually happening. The probability of getting an accident is low, but sometimes you do get an accident, even though the probability was low. What it actually does is increase your power of observation and free you from tedious work, and then you can concentrate on what it is that humans do best. That the computer is not supposed to be a replacement for humans. The computer is actually a very dreadful human.
One metaphor I was using was to say, look, you have an ocean, and right now you're supposed to catch fish, and you know absolutely nothing about the ocean, except that you would like to find fish, but you know nothing about the currents, about what exists, etc. Essentially, this is something that will tell you, look, I looked for fish for you, I'm a friendly little intern. I found a few places where to me it looks like there could be fish. It does not mean that there's no fish somewhere else. I might have missed some fish, and it does not mean that every zone I've found for sure has fish. Maybe I've made some mistake. You know? Maybe some of it is not really fish, it was just a pigeon. You know? So it does save you a lot of time, but it does not, you know, do your work, and then there's a way of actually going on the ground and checking, and which in the end is essential for continuous supervised learning, right? And if I take not a metaphor this time, but an actual example, I think a lot of this automated pattern recognition is used in medicine, so they're getting excellent results. But they're getting excellent results not by eliminating the existence of cancer specialists, right? But by assisting the cancer specialist by something which does one screening. It's very good at screening patterns. It's its job. It's doing one thing. It's never tired. The fact that there is also the specialist to control, make that great gradual improvement of the model, because you can say, no, that was actually a mistake, or that's one you missed, or whatever. And of course, it saves a lot of time for your cancer specialist to have more time with the patient, to have more time to focus on the treatment, to have more time to read the literature, etc. So it means you get a lot more of your time to do your job better. So
I would say it would make you more efficient and targeted.
It makes you superpower. Right?
You will prevent fire instead of extinguishing fire, and even prevent some complaints if you use these tools. And I shared it in the conference, but I can repeat it. So in construction inspectorate, when I started working there, with some reforms that were necessary. So inspectors were responsible to find illegal constructions. And what they were doing basically is sitting in the car and going somewhere. I mean, anywhere, whatever, somewhere. And they were traveling around Lithuania. It cost a lot of money because they had to be paid, and then they had some fuel to have in their cars. And then we simply started to use drones for some territories where we see the development is happening. It was not an efficient solution because satellite imagery would be better, but well, we didn't know that, or we simply had drones. So we made this video models, and actually Neil is now working for the EPD, and yeah. So what we made is some model, put some data layer, the data points of permits, and then magic happens. You know exactly where illegal construction is, or most probably is. You still can find some very low building permit that was issued in 2002, but most likely it is illegal construction, and it helps. But if you do something that is ML discovered about doing real time with artificial intelligence support, it would be extremely efficient.
What tools are cheap and feasible? Because what Martin told us, okay, we can kind of imagine things and use our imagination and say, this is technically possible. But when we are in kind of reality, which is what I understood, that all the data that we have here, analysis is cheap. I mean, means that we do not need additional efforts, costs of collecting, and Sentinel is also relatively cheap, but with some limitations. What else, in your view, is cheap now or will be cheap tomorrow?
Well, the algorithms are free. Most useful algorithms of artificial intelligence that you will need, either for textual processing or image processing, or generally for data categorization, those you will find as open source software. So you can simply learn Python or R and start playing with those. You can literally do that on a laptop. If you don't want to play with Python or R, and I hear somebody who doesn't want to do that. You can, well, you might have an IT department where you might have geeks happy to try to tackle that. You can also, one trick I used when I was working in shipping company was to contact the nearest research department of a university or technical engineering school and say, don't you have students doing master thesis and would be interested in real-life applications? Usually they love that. You say you have data, they don't. And they really need it. So they will be very happy to get their hand on your data. You can have them sign NDAs if it's needed. So that's a way of doing it. And to conclude, the companies that sell the centralized images, they also sell services around those. And making custom analysis jobs is very typical of what they do. So that can absolutely be arranged.
And how does the services, sorry, because it was just, I think it was part of your question as well. How does the different services of imaging, so the cheapest is what's satellite? More or less, I mean, like if you mention, okay, we have satellite and then we have radar, well, radar can be also, I mean, like, out of all the different...
Well, both radar and the photogrammetry can be satellite or...
Yeah, can be satellite or can be, that's, and I'm trying to explain, yeah, thank you, because I'm tired. Yeah, I mean, which sources will be like more or less, I mean, ballpark figure for years, I mean, that can be calculated, of course. I mean, maybe it's not an answer on the spot, but these services can be calculated.
Okay, it really depends whether do you want to buy a drone and do things in the house, or do you want to share the service? Do you want to patrol every day, every week, every year, or every hour? I don't know.
I want to buy it.
What areas do you want to survey? Do you want to survey the whole of Lithuania, or are there specific spots of interest that you want to check on a regular basis? Or all of this is of interest to get dimensions of what you're looking after. But simply purchasing a subscription for satellite imagery it's the matter of a few thousand euros yearly. So for an institution like that, it would be not impossible budget, and yeah, and then you have the processing stage.
Great. One more question. What would be the highest resolution images? Okay, let me put it the other way around. So, for example, Lithuania and other countries have problems with fly tipping of waste somewhere. And if by magic I have access to highest resolution image of the area for whatever money, and I have daily layers of it. So it means that I can save on driving to this particular place, and from the high resolution image I can detect, okay, I have the kind of construction waste, municipal waste, whatever. And for me, and both, I mean, for the institution and for the country, it's a bargain, because we spend 270,000, I think, on fuel per year. So it means that if I can use images for some part of my journeys, it means I have money to spend on this.
Yeah.
So, in your work, have you come up with any? What is the best resolution image, and how often how often it can be? How frequently?
How many passes you have
Yeah.
there? I actually the number for Ontario in Canada. So I realize it's not the same side of the Atlantic, but for Ontario, for instance, they have a 3 satellite constellation, which is the same number of satellites as Copernicus, and they have, I think, 4 passes a day for each, for the whole of Ontario. So it's probably going to be something like that for Lithuania as well. At the very least, you will have 1 pass for every place in Lithuania within a day. And then the resolution I should check, but that's easy to find. For satellite imagery, you will see things like trees, or you will have a metric resolution at the very least.
So I guess where Giedrius is going is what commercial solution we could get, because we're very well aware of the limitations of Sentinel systems, because we try to combine the Sentinel reader with Sentinel photogrammetry. And in Lithuania we get 2 passes a week of IVR.
Okay.
So the radar, yes, it does penetrate the clouds, but we still will get radar shadows from it, because if, for example, we get a clear cut by the edge of the forest where there are still tall trees, that creates a radio shadow. So we get that. We want to eliminate that, so we use the photogrammetry, an image on top, and there we come up with a problem, because we have clouds in the sky literally most of the year. So that is the problem that we have been facing in our pilot project, trying to detect clear cuts, and it's been quite challenging. So I guess we're looking for other options. LiDAR is amazing, and we try to get currently in Lithuania nationwide a full LiDAR scan every 3 years or so. So maybe that's an option. Have a full scan and then scan only the place where you are actually interested in. But maybe moving away from Copernicus, what are the other options?
There are a number of options. I don't have them on this computer, but on one hand, it's difficult to promote one specific actor, and usually what they will sell is a bundle of data coming from Copernicus and from sometimes NASA sources, and also from some of the commercial actors. So you will get data will be augmented by all those constellations.
But I mean, I guess one thing we could do when looking to the person managing the project and budget to my right, but if it's a request, we could see how much time that would take to do this research. We could do it on your behalf, right? Because I know that it's always a question that, having the time of somebody. So if it's an issue, we can try to contact the commercial providers themselves and on their behalf. Find out and do a price comparison and see what is available for whom and when, etc. I mean, can't have the response like this, but definitely it's feasible. This is market research.
Because what I would like to see is a tire on the ground visible from the sky, and the frequency like every 2 days, every 3 days.
It's waste dumping, right? It is for the waste dumping problem.
Yes.
Yeah, so I was thinking exactly about the.
And for other problems as well. I mean, we have waste management site. We know where things should be, and if we have enough resolution, we can identify problems without going to site.
When we already use it for forestry, we were also discussing and included in the report that we applied in other areas, and we were thinking about waste dumping and waste management. But of course, there are some other areas as well for the future. But I think that we can do the research and provide some update on this.
I mean, there are areas of water bodies where there's already research and tracking how algae, for example, develop because of the not properly cleared waste and Domantas from our team is working on that. So there is a number of things that we can use.
So we have a starting point.
So I would say I see two things we can do as follow-up on our side, right? And, one is if you confirm we can try to do this research. I mean, yeah, it's feasible. And the second is if you have the data sets and existing line of questioning, etc., of the call center. You can share it maybe with a quick translation of what are the fields, and I mean, a translation verified by humans might be a little bit better than a pure machine translation. So just not of those two data fields, and then the typical questionnaire questions, so that we have an idea, and then Emilia can have a look at it and say, does it look like a data set that which I could teach a few tricks, like climbing on my shoulder and catching some peanuts, or nah, this is dumb monkey, sorry, no good monkey. Okay, great. So we get promoted, we get drunk, and we go on vacation. Sorry, that was wrong conclusion.
No, but it's Friday mood already.
Yes.
Thank you everyone for participating in this week training events, and I hope that it was useful and all the presentation that you participated in. And we will continue the project. We will continue with the recommendation report to solve some of the problems that we discussed yesterday about risk-based approach in complaint handling and the constraints that we have on the regulatory side, and solve the problems in the cooperation with